For this video, we're going to talk about how to solve exact differential equations. So before we get started, I want you to recall implicit differentiation. Let's say, for example, that we want to take the derivative with respect to x of x squared plus xy squared. Well, what does that equal to? Well, the derivative of the x squared part is 2x plus, and then I have a product here, x times y squared. This is implicit differentiation because the y depends on x in some sense. So we view xy squared as the product. So we'll take the derivative using the product rule. So we'll get y squared plus 2xy y prime. Okay, so one thing I want you to notice about this is that this part here, 2x plus y squared, is the derivative, the partial derivative, with respect to x of x squared plus xy squared. And the other thing I want you to notice is that this 2xy, what's that? That's the partial derivative with respect to x of x squared plus xy squared. So I have this partial derivative with respect to x plus the partial derivative with respect to y, y prime. So that's what we see. Okay, let's try another one. What if I took the derivative with respect to x of y sine x plus x squared e to the y minus y? Okay, so I'm going to take the derivative of this. Again, the first part is a product, so I'm going to do sine x times y prime plus, so then I'm going to do y cosine x, okay, and then I'm going to do plus, and now I'm going to take the derivative of this second term. Again, it's a product, so I'll have 2x e to the y plus x squared, and then the derivative of e to the y with respect to x is e to the y, y prime. And then I'll do minus, and the derivative of y, again with respect to x, is y prime, or dy dx. Okay, let's rearrange these terms here. Oop, I have a little extra thing here. Let's delete. There we go. So I'm going to rearrange these terms. I'm going to put all the things with y prime in them together, and all the things without it I'll move to the front here. So I'll have y cosine x plus 2x e to the y, and then I'll have plus, and then I have sine x plus 2x squared e to the y minus 1 y prime. And so what I want you to notice here is, again, this first part is the partial derivative with respect to x of y sine x plus x squared e to the y minus y. And this part here is the partial derivative with respect to y of y sine x plus x squared e to the y minus y. So we have the partial derivative with respect to x of the original function plus the partial derivative with respect to y of the original function times y prime. So here is a generalization of what the pattern that we're seeing here. Now again, I'm not going to present it with a proof, but I'll just give you this generalization that the derivative with respect to x of some function, I'll just call it psi of xy, is going to be equal to the partial derivative of psi with respect to x plus the partial derivative of psi with respect to y times y prime. Okay, so let's say we want to solve this differential equation. So I already talked about this example a little bit, and we noted, so let's write a solution. Okay, so some of the methods that we've had thus far is we've talked about linear differential equations. Is this a linear differential equation? I claim that it's not a linear differential equation because I have this y squared here. So it's not a linear differential equation. And is it separable? Well, I claim that it's not separable as well. But I'll leave that for you to check. But one thing we can do is we can observe, and this is based on the previous discussion we just had, we can observe that phi of xy equals x squared plus xy squared has the property that the partial derivative of phi with respect to y is equal to with respect to x, is equal to 2xy squared plus y squared, and the partial derivative of phi with respect to y is equal to 2xy. So this is, we talked about this a little bit previously. Thus, this 2x plus y squared plus 2xy y prime equals 0 is the same thing as the derivative with respect to x of this function, x squared plus xy squared equals 0. And so if I integrate both sides, with respect to x, then what do I get? Well, I get x squared plus xy squared is equal to, what's the integral of 0 with respect to x? It's just some constant. So this is my general solution. Now, it may not be super satisfying to look at this because you kind of want to solve for y, but you can't always solve for y. So it would be nice if we could solve for y, but you can't always. In this case, you kind of can. So that's the idea. Okay, so you start with this differential equation. You figure out that that left-hand side is the derivative with respect to x of some psi function, which is a function of x and y. Then, if I can write this differential equation as the derivative of some function of x and y, then I can integrate both sides with respect to x, and I'm done. Okay, well that sounds easy enough, but the question is, how do we find the psi of xy? So the key to that is to recall from Calculus 3 that if psi of xy is continuous, the second order mixed partial derivatives are equivalent. So what do I mean by that? So if psi of xy is continuous, and we're going to be mostly dealing with things that are friendly in this course, then the partial derivative with the second order partial of psi with respect to x and then y, okay, let me start over. The second order partial of psi with respect to x and then y, it needs to be equal to the second order partial with respect to y and then x. So this was a theorem that you learned from Calculus 3, that if you took this, first take the derivative with respect to x and then with respect to y, that should be the same thing as if I take the partial derivative with respect to y and then with respect to x. So that's going to be the key to finding this psi. Okay, so here's the theorem. So we're going to let the functions m, n, my, nx be continuous in the rectangular region R. Then we have that m x y plus n x y y prime equals 0 is a differential equation that is exact in R if, and only if, the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. In this case, there exists a function psi of xy satisfying that psi, the partial derivative of psi with respect to x, is equal to m, and the partial derivative of psi with respect to y is equal to n. And the general solution to the exact differential equation is psi of x, y equals c. So let's take a minute to discuss what this is saying. So if we have a differential equation of this form, where we have this function of x and y plus another function of x and y times y prime equal to 0, something like this is exact if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And in this case, there is a psi. So this psi is kind of like my top level function. So I'm going to draw this. And then the partial derivatives of psi, what are the partial derivatives of psi? I have psi, the partial derivative with respect to x of psi is m. And the partial derivative of psi with respect to y is n. So what is the partial derivative of n with respect to x? Well, that's the second order partial of psi with respect to y first, then x. So the partial derivative of n with respect to x is a second order partial of psi. And the partial derivative of m with respect to y is a second order partial of psi with respect to x first and then y. Right? So that's why these two have to be equivalent, because they are second order mixed partials. Okay, so if you have these second order mixed partials that are equivalent, then that means there exists this psi functions. Okay. So how do we use this theorem? Well, the first thing we want to do is we want to check for exactness. So if we're given a function of the form m x y plus n x, y, y prime, the first thing we want to check is we want to check that m y, the partial derivative of m with respect to y, is equal to n x. If they're not equal, then the differential equation is not exact, and we either need to use a different method or maybe we can't solve it. So the second case, if it is exact, then we can choose to either integrate m with respect to what? What is m now? M is the partial derivative of psi with respect to x, right? So we want to integrate m with respect to x to get back to that psi. Or we could integrate n with respect to what? What do I want to integrate n with respect to? Well, what is n? N is the partial derivative of psi with respect to y. So I need to integrate n with respect to y to get back to my psi. Okay. Then I want to take, so let me just say one more thing here. So either of these will give us the psi, almost. And why do I say almost? Well, if I integrate m with respect to x, I might have some portion of my psi that only had y's in it. So when I took the derivative with respect to x, those terms in the psi that had y's in it went away. So it will almost give us the psi. So once we have that, we want to take the derivative of that psi that we have and set it equal to, either we want to take the derivative with respect to y of the integral of m with respect to x, and we want to set that equal to, so if I integrate m with respect to x, then that would get me back up to the psi, and then I take the derivative of the psi with respect to y, that should be equal to n. Because what is n? N is the partial derivative of psi with respect to y. Or we can take the derivative with respect to x of the integral of n with respect to y. That should be equal to m. Okay? And then we're going to solve for our h of y or h of x by integrating h prime of x or h prime of y. Okay. Now, and that step will make more sense when I do an example. Now, you should have your function psi of xy. So the general solution is psi of xy equals c. So here's an example. We're going to solve this differential equation. So the first thing we want to do for our solution is we're going to check for exactness. Okay, so this thing here is my m. This guy here is my n, right? So I want to check that m, the partial derivative of m with respect to y. What is my? Well, it's going to be cosine x plus 2x e to the y. And what is nx going to be equal to? Well, the partial derivative of sine x with respect to x is cosine x, plus the partial derivative of x squared e to the y with respect to x is 2x e to the y. And then the derivative of 1 is 0 with respect to x. So I have that those two things are equal, so I know that this equation is exact. Okay, so what does that mean? Thus, this psi of xy exists. And we know that and psi, the partial derivative of psi with respect to x is equal to m, and the partial derivative of psi with respect to y is equal to n. Okay, so I have a choice here. I can choose to integrate m with respect to x or n with respect to y. Now, how do you choose which one to do? Well, you can think about, there's a little bit of strategy in choosing which one you want to do. I'm going to make kind of the less efficient choice, and I'm going to choose to integrate m with respect to x here, and I'm choosing to do it that way because I want to make a point. So I'm going to choose to integrate m with respect to x here, okay? So the integral, so that psi of xy is going to be the integral of m with respect to x. Okay, what is that integral? I'm going to get y sine x plus x squared e to the y, and then I could have some term here, h of y, that went away when I took the derivative with respect to x. So I could have this some other thing with y. So look at this. I almost have my phi, right? Okay, I have my phi of xy is equal to that. So I have most of the terms of my phi. The only thing I'm missing is any part of my phi that had y's in it and no x's. So at the next step, I'm going to do something to figure out what that h of y could be. So what I'm going to do in this third step is I'm going to take the derivative the partial derivative with respect to y now. So what is the derivative with respect to y? So the derivative of psi with respect to y is going to be equal to sine x plus x squared e to the y plus h prime of y. So I just took the derivative with respect to y of the thing I had up there. But what is the partial derivative of psi with respect to y anyway? Well, that should be equal to n, right? That should be equal to my n of xy. Well, what is my n of xy? It's sine x plus x squared e to the y minus 1. So what does that tell me? That tells me that this h of y here, h prime of y, needs to be equal to that minus 1. So I know h prime of y is equal to minus 1. So if I integrate that with respect to y, I get that h of y is equal to negative y. So now I have my whole psi. So what is my psi? My psi of x, y is what I had up here before, right? This thing. It's equal to y sine x plus x squared e to the y plus, and then what is my h of y? It's negative y. Oh, so I should have put